Right now, at this very moment, somewhere in the universe, a bubble might be forming. Not a bubble of air or water, a bubble of true vacuum, a region of space where the fundamental nature of reality itself is different, where the laws of physics have changed, where atoms cannot exist. This bubble, if it exists, is expanding at the speed of light. Nothing can outrun it. Nothing can stop it. And when it reaches us in 1,000,000 years or 1,000 or tomorrow, everything we know will cease to exist in less than a microsecond. Not gradually, not mercifully. Every atom in your body, every planet, every star, every galaxy reconfigured into something unrecognizable. A universe where chemistry is impossible, where stars cannot shine, where life in any conceivable form cannot exist. Physicists call this vacuum decay, the hypothesis that our universe might be sitting in a false vacuum, a temporary metastable state waiting to collapse into the true vacuum like an avalanche waiting for a trigger. And here's what keeps cosmologists awake at night. The mathematics suggests it's not just possible, it might be inevitable. In 2012, after the Higgs boson discovery at CERN, physicists calculated the stability of our universe. The answer was unsettling. We're living on a knife's edge. Our universe is metastable, stable for now, but vulnerable to catastrophic collapse. Today, we journey through the quantum mechanics, the cosmology, and the existential terror of the universe's most perfect death. What you're about to discover will transform your understanding of stability, time, and the fundamental fragility of existence itself. In 1964, physicist Peter Higgs proposed something radical. Empty space isn't empty. Throughout the universe, pervading every cubic centimeter of vacuum, there exists a field, the Higgs field. This field gives particles their mass. Without it, electrons would travel at light speed. Atoms couldn't form. Matter as we know it wouldn't exist. But here's the critical insight. Fields have potential energy. And like a ball sitting in a landscape of hills and valleys, the Higgs field seeks the lowest energy state it can find. Imagine a ball sitting in a valley. It's stable there, but if that valley isn't the deepest valley in the landscape, if there's a lower valley somewhere else, separated by a hill, the ball is only temporarily stable. It's in what physicists call a false vacuum. The ball could, through quantum tunneling, suddenly find itself in the deeper valley, and when it does, the change cascades outward at the speed of light, transforming everything. This isn't just abstract theory. This is our universe. In 2012, when scientists at CERN's Large Hadron Collider discovered the Higgs boson, they measured its mass, approximately 125 GeV, or giga-electronvolts. That number matters a lot. Dr. Joseph Leiken from Fermilab and Dr. Gianfrancesco Giudice from CERN immediately ran calculations using this measured mass. They computed the Higgs field potential, the landscape of valleys and hills. The result was published in 2013. Our universe appears to be metastable. The Higgs field is not in the lowest possible energy state. There exists a lower state, and our current state could, theoretically, decay into it. In other words, the ball is sitting in a false vacuum, and there's a deeper valley waiting. But how could the universe suddenly jump from one state to another? The answer lies in quantum mechanics, specifically quantum tunneling. In classical physics, a ball in a valley can't escape unless it has enough energy to roll over the hill. But quantum mechanics allows for something stranger. At quantum scales, particles don't have definite positions. They exist as probability waves, and these waves can tunnel through barriers that should be impenetrable classically. Quantum tunneling is real. We observe it constantly. Radioactive decay, particles tunnel out of atomic nuclei, scanning tunneling microscopes, electrons tunnel between surfaces, fusion in the sun. Hydrogen nuclei tunnel through electrical repulsion to fuse. It's not speculation, it's verified physics, confirmed billions of times in labs worldwide. Now, apply this to the Higgs field. At any point in space, at any moment, the Higgs field could spontaneously tunnel from its current false vacuum state to the true vacuum state. The probability is incredibly small, vanishingly tiny for any given point in space-time. But the universe is vast, and it's been around for 13.8 billion years. Dr. Sidney Coleman from Harvard University, in his landmark paper, The Fate of the False Vacuum in 1977, calculated that in an infinite or sufficiently large universe, vacuum decay is not just possible, it's inevitable. Somewhere, sometime, the tunneling will occur, and when it does, a bubble of true vacuum forms. Inside the bubble, the laws of physics are different. The Higgs field has a different value. Particle masses change, the strength of fundamental forces changes, the structure of atoms, if they can exist at all, is altered beyond recognition. But here's the terrifying part. The bubble doesn't stop, it grows. The bubble wall moves at the speed of light, or more precisely, at exactly the speed of light. It's a first-order phase transition propagating through space-time. As the bubble expands, everything it touches is converted. Matter reorganizes according to the new physics, stars implode or explode, atoms disintegrate, complex structures dissolve. The universe inside the bubble isn't just hostile to life, it's a fundamentally different universe with different physics. Dr. Max Tegmark from MIT calculated what happens to matter at the bubble wall. The energy released during the phase transition is enormous, comparable to the energy density of the early universe moments after the Big Bang. Everything at the boundary is essentially vaporized by the energy of the transition itself before experiencing the new physics. You wouldn't see it coming. Information can't travel faster than light, and the bubble wall moves at light speed. One moment you exist, the next moment, no transition, no experience, you simply don't exist anymore. From outside the bubble, observers, if any survived, would see a sphere of destruction expanding outward, consuming everything: planets, stars, galaxies, an unstoppable wave of altered reality. And there's no way to stop it. The 2012 Higgs discovery confirmed our universe is metastable, but it also revealed something hopeful. We're probably safe, for now. Dr. Decay and Dr. Lycan calculated the lifetime of our false vacuum. Using the measured Higgs mass and top quark mass, they estimated how long it would take, on average, for vacuum decay to occur somewhere in the observable universe. The answer? Approximately 10 to the 100 years. That's incomprehensibly long. The current age of the universe is only 1.38 times 10 to the 10 years. The sun will die in 5 billion years, or 5 times 10 to the 9th years. Even the last stars will burn out in around 10 to the 14 years. 10 to the 100 is so far in the future that all stars will have died, all black holes will have evaporated, and the universe will be cold, dark, and essentially dead long before vacuum decay becomes probable. So we're safe, right? Not necessarily. The calculation assumes nothing disturbs the false vacuum, but several things could trigger decay much sooner. Number 1, high-energy particle collisions. If particles collide with enough energy, they could provide the kick needed to initiate tunneling. Number 2, black holes. The extreme conditions near black hole event horizons might catalyze vacuum decay. Number 3, cosmic inflation. During the Big Bang's inflationary period, the universe underwent a previous false vacuum decay. Could it happen again? Number 4, unknown physics. We might be wrong about the Higgs field potential. Future discoveries could reveal the true vacuum is closer than we think. In 2015, Dr. William East and colleagues ran simulations of collapsing massive black holes. They found that under certain conditions, the extreme energies could potentially nucleate a vacuum decay bubble. The probability is still tiny, but it's not zero. But the evidence forces us to confront an uncomfortable possibility. Our universe's stability is not guaranteed, it's contingent, temporary, and the end, when it comes, will be absolute. The most direct evidence for metastability comes from precision measurements at CERN. The Higgs boson mass was measured at 125.25 plus or minus 0.17 GeV. This measurement, refined over years of data collection from quadrillions of particle collisions, is remarkably precise. Combined with the top quark mass, 173.0 plus or minus 0.4 GeV, these values allow physicists to calculate the shape of the Higgs potential, the energy landscape. Dr. Dario Buttazo led a team in 2013 that performed the most detailed analysis. Their conclusion? The measured values place our universe near the boundary between absolute stability and metastability. We appear to be metastable with a small but non-zero probability of vacuum decay. The critical insight? If the Higgs mass had been just 1 to 2 GeV different, our universe would be either absolutely stable, higher mass, or catastrophically unstable, lower mass. We're living on a knife's edge. And there's no reason why the Higgs mass should be this particular value. It's not predicted by theory, it's simply measured. The universe could have had different values, and if it did, we might not be here to observe it. This is anthropic reasoning. We observe a metastable universe because only a metastable or stable universe could produce observers. If the universe were highly unstable, vacuum decay would have occurred long ago, preventing the formation of galaxies, stars, and life. We exist because we got lucky with the cosmic dice roll. Vacuum decay isn't pure speculation. We know it's happened before. The universe has already undergone at least 2 major phase transitions. The electroweak phase transition, 10 to the negative 12 seconds after the Big Bang. At extremely high temperatures, the electromagnetic and weak nuclear forces were unified. As the universe cooled, it underwent a phase transition, a vacuum decay event, where these forces separated. This transition involved the Higgs field settling into its current non-zero vacuum expectation value, giving particles their masses. Cosmic inflation, 10 to the negative 36 seconds after the Big Bang. The inflator field, another hypothetical field, decayed from a false vacuum to a true vacuum, releasing enormous energy and causing the universe to expand exponentially. In less than 10 to the negative 32 seconds, the universe grew from smaller than an atom to larger than a galaxy. This was a vacuum decay event on cosmic scales. Dr. Alan Guth, who proposed cosmic inflation in 1981, showed that phase transitions in quantum fields could drive exponential expansion. The mathematics is identical to vacuum decay, except inflation happened so early that no complex structures existed to be destroyed. The point? Vacuum decay is not theoretical speculation. It's happened multiple times in our universe's history. The question is, could it happen again? And if so, would it be the final phase transition? Here's one of physics's deepest mysteries. Why is the vacuum energy so small? Quantum field theory predicts that empty space should have enormous energy, vacuum energy arising from quantum fluctuations. The predicted value, based on fundamental physics, is approximately 10 to the 120th times larger than the observed value. This is called the cosmological constant problem, and it's perhaps the worst prediction in physics history. The observed vacuum energy, measured through the universe's accelerating expansion, is incredibly tiny, but not zero. It's often called dark energy. But here's the connection to vacuum decay. The cosmological constant represents the energy density of the vacuum. In our false vacuum, it has one value. In the true vacuum, it would have a different value. Dr. Steven Weinberg in 1987 pointed out something remarkable. If the cosmological constant were much larger, even by a factor of 10, the universe would expand so rapidly that galaxies couldn't form. If it were negative, the universe would recollapse. We observe a very small positive value, and this constrains the possible vacuum states. Our false vacuum has a cosmological constant that allows structure formation. The true vacuum might not. It might have a cosmological constant that causes immediate collapse or exponential expansion, or simply prevents atoms from existing. This fine-tuning, the fact that our vacuum state allows life, suggests we might be in an anthropically selected false vacuum. We exist in this particular state not because it's the lowest energy state, but because it's one of the few states that permits observers. The standard model of particle physics, our most successful theory of fundamental forces, makes specific predictions about vacuum stability. Using the measured Higgs and top quark masses, physicists can calculate the beta function, how the Higgs field's coupling strength changes with energy. At low energies, ordinary matter, the Higgs field is stable, but calculations show that at extremely high energies, around 10 to the 10 GeV, far beyond what any collider can reach, the coupling becomes negative. This means the Higgs potential develops an instability at high energies. The valley we're in connects to a deeper valley through a high-energy regime. Dr. Mikhail Shapushnikov and colleagues published detailed calculations in 2015 showing this energy-dependent behavior. They concluded The standard model remains valid up to the Planck scale, but only if we accept metastability. This has profound implications. In the early universe, temperatures were high enough to access these unstable regions. How did the universe survive without decaying immediately? One possibility, cosmic inflation. If inflation occurred before the universe cooled enough to enter the unstable regime, it might have inflated away any early vacuum decay bubbles, leaving us in a metastable but temporarily safe state. Another possibility, we got lucky. Quantum fluctuations during the Big Bang could have placed us in a fortunate configuration where decay hasn't occurred yet. But this represents just one piece of a much larger puzzle hidden in the quantum structure of space-time itself. In 2015, Dr. Philip Berta, Dr. Ruth Gregory, and Dr. Ian Moss published a disturbing paper, Gravity and the Stability of the Higgs Vacuum. They showed that black holes, particularly large rotating black holes, could act as catalysts for vacuum decay. Here's why. Near a black hole's event horizon, gravity is so intense that space and time behave strangely. The Higgs field, like everything else, is affected by this curvature. In regions of extreme gravitational stress, the energy barrier between false vacuum and true vacuum becomes thinner. The probability of quantum tunneling increases dramatically. Their calculations suggested that supermassive black holes, the kind at the centers of galaxies, could potentially nucleate vacuum decay bubbles. The larger the black hole, the greater the risk. The supermassive black hole at the center of our Milky Way, Sagittarius Asterisk, has a mass of 4 million suns. The one in M87 has a mass of 6.5 billion suns. But even these monsters present only a tiny risk. The probability of nucleating vacuum decay is still incredibly small. However, in the early universe, conditions were different. During the Big Bang, primordial black holes might have formed with extreme properties. If any still exist today, they could pose a greater risk. And here's the disturbing part. When a massive black hole eventually collapses during its final moments of evaporation, the energy densities involved could potentially trigger vacuum decay as a final act. We wouldn't know. By the time we observed it, the bubble would already be expanding towards us at light speed. Why is our universe metastable rather than absolutely stable or catastrophically unstable? One possible answer, the anthropic principle, combined with the multiverse hypothesis. If eternal inflation is correct, a variant of cosmic inflation proposed by Dr. Alan Guth and Dr. Alexander Vilenkin, then our universe is just one bubble in an infinite multiverse of bubble universes. Each bubble forms through a vacuum decay event during inflation. Each has different physics constants, different vacuum energies, different fundamental forces. Most bubbles have physics that don't support life. Maybe their cosmological constant is too large, preventing galaxy formation. Maybe their Higgs field value makes atoms impossible. Maybe they decay immediately into true vacuum. But in an infinite multiverse, some bubbles, like ours, have the right properties for complexity, chemistry, and life. We observe a metastable universe not because metastability is privileged, but because we can only exist in universes that are at least metastable. This is called anthropic selection. Dr. Steven Weinberg used this reasoning in 1987 to predict the approximate value of the cosmological constant before it was measured. His anthropic argument suggested it should be small but positive, which was later confirmed by observations of the universe's accelerating expansion. If the anthropic principle explains our metastability, it carries a disturbing implication. Our universe is not special. It's one of countless universes, most of which have already decayed or will decay soon. We simply happen to live during the brief window when our particular bubble hasn't decayed yet. And that window could close at any moment. Here's a comforting thought. If high-energy particle collisions could trigger vacuum decay, the universe has already performed that experiment trillions of times. Cosmic rays, high-energy particles from space, constantly bombard Earth and other planets. The highest energy cosmic rays exceed 10 to the 20 electron volts, far more energetic than anything the Large Hadron Collider produces. These particles have been hitting planets, moons, and asteroids for billions of years throughout the observable universe. If particle collisions could easily trigger vacuum decay, it would have happened long ago. The fact that we're still here suggests vacuum decay isn't easily triggered, at least not by particle collisions at energies we've naturally observed. Dr. Gia Diwali and colleagues in 2009 used this cosmic ray argument to constrain the probability of vacuum decay. Their conclusion: natural particle collisions have already tested energies up to 10 to the 20 eV without triggering vacuum decay. This suggests any instability lies at higher energies or has extremely low probability. This is reassuring, but only partially. First, while cosmic rays reach high energies, they're individual particles. The LHC creates collisions with high center of mass energy in controlled, concentrated environments. The physics might differ. Second, black holes create even more extreme conditions than cosmic rays. Near an event horizon, space-time curvature reaches Planck scale intensities. These conditions have no equivalent in cosmic ray physics. Third, the anthropic selection argument applies. If cosmic rays commonly triggered vacuum decay, we wouldn't be here to observe them. The fact that we exist means we're in a universe, or a region of multiverse, where decay hasn't occurred. Yet. So, cosmic rays provide some reassurance. The 10 to the 100-year lifetime estimate for our false vacuum comes with enormous uncertainties. Dr. Giudice's 2013 calculations depend on several assumptions. 1. The standard model is complete. If new physics exists beyond the standard model, new particles, new forces, new fields, they could dramatically change the vacuum stability calculation. 2. Precise mass measurements. The calculation is sensitive to exact values of Higgs and top quark masses. Small measurement errors could shift the result by orders of magnitude. 3. No quantum gravity effects. The calculation uses quantum field theory in curved spacetime, but doesn't include a full theory of quantum gravity. Near Planck scale energies, quantum gravity effects could alter the Higgs potential. 4. No environmental triggers. The calculation assumes nothing disturbs the vacuum except quantum fluctuations. External factors, black holes, high-energy processes, unknown physics could dramatically increase decay probability. In 2018, Dr. Quarry and Dr. Matsui recalculated vacuum stability, including gravitational effects. Their conclusion: when gravity is included, the lifetime could be orders of magnitude shorter. The false vacuum might be less stable than previously thought. Other physicists have suggested the opposite. Maybe undiscovered particles, like supersymmetric partners, stabilize the vacuum, making it absolutely stable rather than metastable. The point is, we don't know for certain. The 10 to the 100-year lifetime estimate is a central value with huge error bars. The true lifetime could be 10 to the 200 years, effectively eternal. Or it could be 10 to the 50 years, or 10 to the 20 years. We simply don't know. The evidence extends beyond theoretical calculations into the realm of cosmic destiny and existential uncertainty itself. Let's be precise about what happens during vacuum decay. The process has 3 stages. Stage 1, nucleation. Somewhere in space, quantum tunneling occurs. A tiny region, perhaps Planck scale, 10 to the minus 35 meters, spontaneously transitions to true vacuum. The probability is governed by the Euclidean action, a mathematical object describing how likely the transition is. The larger the barrier between false and true vacuum, the less likely the tunneling. Stage 2, expansion. The true vacuum bubble, once formed, has lower energy density than the surrounding false vacuum. This energy difference creates outward pressure. The bubble wall accelerates to the speed of light. It cannot accelerate beyond light speed. That would violate special relativity, so it moves at exactly c. The wall thickness is microscopic, perhaps only 10 to the minus 15 meters, but the destruction it causes is total. Stage 3, conversion. As the bubble expands, everything it encounters is converted. The Higgs field adopts its true vacuum value. Particle masses change instantly. Fundamental constants shift. Atoms, if they can exist in the new physics, would have different sizes, different chemical properties, different nuclear binding energies. Stars inside the bubble, if any survived the transition energy, would behave completely differently. Fusion rates would change, stability conditions would change. Most would likely collapse or explode. The energy released during vacuum decay is enormous. The energy difference between false and true vacuum, call it delta rho, is comparable to grand unified theory scales, approximately 10 to the 16 GeV per cubic centimeter. When the bubble wall passes through matter, this energy is released locally. Dr. Sidney Coleman calculated the energy flux at the bubble wall. For reasonable vacuum energy differences, the energy density exceeds that of matter by factors of 10 to the 40 or more. In practical terms, as the bubble wall passes through you, the energy released would be equivalent to a matter-antimatter annihilation of your entire body, concentrated in a microsecond. You wouldn't experience pain. There wouldn't be time. Neural signals travel at meters per second. The transition happens at light speed. You would simply cease to exist, your constituent particles reorganized according to different physical laws. For Earth, the passage would be even more dramatic. The planet's binding energy, the energy holding it together gravitationally, is about 10 to the 32 joules. The vacuum decay energy passing through Earth would be roughly 10 to the 40 joules. Earth wouldn't explode, it would evaporate. Every atom simultaneously converted, releasing enough energy to unbind the planet millions of times over. The Sun would fare similarly. Its fusion processes would halt instantly. The change in particle physics might cause immediate collapse or expansion, depending on how the new vacuum's constants affect stellar structure. Within minutes, the entire solar system would be unrecognizable. Could anything survive inside the bubble? Possibly. If the true vacuum allows atoms, perhaps with different binding energies and chemical properties, then some form of matter might exist. But it wouldn't be our matter. Dr. Lisa Randall from Harvard has explored how different vacuum states affect fundamental constants. Her work suggests that small changes in the Higgs field value could make atoms much larger or smaller, make chemistry faster or slower, or even prevent stable nuclei from existing. One possibility, the true vacuum has a Higgs field value near zero. In this case, particles would be massless or nearly massless. Atoms couldn't form. Matter consists of light-speed particles incapable of binding into structures. Another possibility, the cosmological constant in the true vacuum is large and negative. Space-time itself would be unstable, collapsing toward a big crunch. Or perhaps the true vacuum's physics allows completely different forms of complexity. Maybe the new physics permits structures we can't imagine, not atoms, not molecules, but something else entirely. We can't know. The physics inside the bubble is determined by the true vacuum's parameters, which we haven't measured because we've never accessed the true vacuum. All we know is whatever exists inside wouldn't be recognizable to us. It would be a genuinely alien universe, born from our universe's corpse. This forces us to reconsider fundamental assumptions about permanence, stability, and the continuity of physical law. Imagine a vacuum decay bubble has formed somewhere in the universe. It's expanding toward us at light speed. Can we detect it before it arrives? The answer, no. By definition, information cannot travel faster than light. The bubble wall moves at light speed. Therefore, no signal can outrun it to warn us. The first indication that a vacuum decay bubble is approaching would be its arrival. 1 microsecond, you're reading this. The next microsecond, you don't exist. No warning, no chance to prepare, no final thoughts. But maybe we could see indirect effects? If the bubble formed nearby, say within our galaxy, we might observe the destruction of distant stars before the bubble reaches us. We'd see stars suddenly wink out, not because their light is blocked, but because they've been converted into whatever exists in the true vacuum. The darkness would spread across the sky like an expanding circle, consuming every star, every galaxy in its path. We might have days, months, or years to watch it approach, knowing it's unstoppable. Dr. Max Tegmark calculated the psychological impact. A vacuum decay bubble visible in the sky would be the ultimate existential crisis. Humanity would watch its own inevitable extinction approaching at light speed. Some physicists have speculated about using gravitational waves as an early warning system. Gravitational waves travel at light speed, same as the bubble, but they might be emitted from the bubble wall as it distorts spacetime. But even if we detected gravitational waves from an approaching bubble, the waves would arrive simultaneously with the bubble itself. No advance warning. The cosmos would give us no chance to say goodbye. Let's say we detect a vacuum decay bubble approaching. Perhaps we see it consuming distant galaxies. Can we do anything? The answer is almost certainly no. The bubble wall moves at light speed and carries energy densities exceeding anything in the material universe. No known material could withstand it. No conceivable technology could stop it. But physicists have explored hypothetical possibilities. Option 1, create a counterbubble. If we could intentionally nucleate our own vacuum decay bubble, perhaps one that transitions to a different true vacuum, the two bubbles might collide and do something. Maybe they annihilate each other, maybe they merge, maybe one converts the other. Dr. Sidney Coleman explored bubble collisions mathematically. His conclusion? Bubble collisions in quantum field theory are extraordinarily complex. Predicting outcomes require knowledge we don't have. In practice, deliberately nucleating vacuum decay would be insane. We'd be destroying ourselves to potentially stop a process that might destroy us anyway. Option 2, manipulate spacetime. If we could create a region of intense gravitational curvature, perhaps using exotic matter or controlled black holes, we might bend spacetime enough to deflect the bubble. But this requires technology far beyond anything humanity possesses or can imagine. We'd need to manipulate the fabric of reality itself, using energies comparable to those in the bubble wall. And even if possible, we'd need years or centuries to build such device. The bubble might arrive before we finish. Option 3, escape to a parallel universe. This is pure speculation, but if the multiverse is real, and if there's some way to transition between universes via wormholes or higher dimensions, maybe a civilization could escape an incoming bubble by jumping to another universe. Of course, that other universe might have its own vacuum decay risks. You'd be fleeing one death for another. The realistic answer? Nothing. We can't stop it. We can't escape it. We can't even see it coming. If vacuum decay begins anywhere in the observable universe, our fate is sealed. But let's zoom out. Assume vacuum decay doesn't happen in the near term. What about the far future? In 10 to 100 years, when the false vacuum naturally decays, what will the universe look like? All stars will have burned out by 10 to the 14 years. All white dwarfs will have cooled to black dwarfs by 10 to the 15 years. Even black holes will have evaporated through Hawking radiation by 10 to 100 years. The universe will be cold, dark, and nearly empty, just isolated particles and photons separated by ever-increasing distances as expansion continues. In this far future, vacuum decay would find almost nothing to destroy. The bubble would expand through a nearly empty universe, converting vacuum from one state to another, but encountering virtually no matter. Would it matter? Would the phase transition have any observable effects if there's nothing to observe? Dr. Freeman Dyson speculated about this in his 1979 paper, Time Without End. He suggested in the far future, intelligent civilizations might exist as ultra-slow thinking entities spreading across vast distances to minimize energy consumption. If such entities exist when vacuum decay finally occurs, they would be destroyed instantly, no matter how slow they're thinking, no matter how carefully they conserved energy. Recent breakthroughs suggest we might understand vacuum decay better in coming decades. The LHC's high luminosity upgrade, beginning in 2029, will make more precise measurements of the Higgs boson and top quark. If we discover new physics, supersymmetry, extra dimensions, new particles, our understanding of vacuum stability could change dramatically. The proposed future circular collider, if built in the 2040s, could explore even higher energies, potentially testing the vacuum stability directly. But every experiment carries a question. Could we accidentally trigger what we're trying to study? In 2008, before the LHC turned on, physicists published a safety review. Their conclusion: colliders cannot trigger vacuum decay because cosmic rays have already performed this experiment at higher energies without incident. That reassurance stands, but future colliders will reach unprecedented energies, closer to the grand unified theory scale where instabilities emerge. Will we eventually build a machine that pokes the false vacuum hard enough to trigger its collapse? Probably not. The energies required are still 10 orders of magnitude beyond any foreseeable technology. But probably not isn't definitely not. What does it mean, psychologically and philosophically, to know our universe is metastable? For most of human history, we assumed the laws of physics were eternal. Sure, the sun would die, the earth would end, but the fundamental structure of reality, atoms, forces, space, time, would persist forever. Vacuum decay eliminates that assumption. The laws of physics are temporary, contingent. They could change without warning, not because we discovered new science, but because the universe itself transitions to a different state. Dr. John Leslie, philosopher of existential risk, argues this changes ethical calculations. If humanity could exist for only 10,000 more years before vacuum decay, would our long-term projects matter? Should we still care about the far future if the far future might not exist? But the 10 to the 100-year timescale is so vast that vacuum decay shouldn't affect our near-term decisions. By any practical standard, the universe is stable for all timescales relevant to human civilization. Yet, the knowledge itself carries weight. We live in a precarious universe. Existence is borrowed time. Some find this terrifying. Others find it liberating. If the universe is temporary, perhaps impermanence isn't a bug, it's a feature. Change, flux, impermanence might be fundamental to reality. Buddhism teaches that all composite things are impermanent. Vacuum decay suggests even the laws of physics are composite things, assembled from quantum fields in metastable configurations, destined to change. Here's a deeper puzzle. Why did we evolve consciousness during the metastable period? If the universe existed for 10 billion years before Earth formed, and will exist for 10 to the 100 years after, why does intelligent life emerge during this infinitesimally brief window when the universe is metastable but hasn't decayed? One answer: anthropic selection. Intelligent observers can only exist during periods when the universe supports complexity. After vacuum decay, complexity is impossible, so of course we find ourselves before decay. We couldn't exist after. But this raises disturbing questions about future civilizations. If humanity survives and spreads across the galaxy, our descendants in 10 million years will also live in a metastable universe, and their descendants in 100 million years, and theirs in 1 billion years. For 10 to the 100 years, civilizations could rise and fall, each living in the shadow of eventual vacuum decay, each knowing their existence is temporary. Unless we're wrong about metastability, unless measurements change, unless new physics stabilizes the vacuum, or unless the multiverse is real and civilizations can somehow escape from a decaying bubble to another universe. These are profound questions at the intersection of physics, philosophy, and cosmic destiny. Could a sufficiently advanced civilization intentionally trigger or prevent vacuum decay? Dr. Sidney Coleman explored this mathematically. In principle, if you could concentrate enough energy in a small enough region, creating conditions similar to the early universe, you might nucleate a decay bubble. But the required energies are staggering. You'd need to concentrate the mass energy of an entire star into a volume smaller than an atom. No plausible technology could achieve this. But what about a Type 3 civilization on the Kardashev scale? One that commands the energy of an entire galaxy. Such a civilization might, in principle, construct an experiment capable of probing vacuum stability directly. They might even attempt to trigger a controlled decay bubble as a weapon, or as a means of escaping to a new universe with different physics. The dark implication, if advanced civilizations exist elsewhere in the universe, and if one of them triggers vacuum decay, intentionally or accidentally, every other civilization dies. This connects to the Fermi paradox. Maybe advanced civilizations are rare not because intelligence is rare, but because intelligent species eventually develop technology capable of triggering vacuum decay. Most civilizations destroy themselves and much of the universe through experiments gone wrong. We might be living in a particularly fortunate region of space-time, in a universe where no one has yet triggered the ultimate catastrophe. Or maybe we're the first intelligence in our universe capable of asking these questions. And maybe our answers will determine whether the universe remains stable or whether we accidentally end everything. The most profound implications emerge when we consider whether intelligence itself, consciousness, curiosity, scientific inquiry, might be the universe's greatest threat to its own stability. Vacuum decay is the ultimate existential risk, not just to humanity or Earth or even our galaxy, but to the entire universe. When it happens, if it happens, everything ends. Not through heat death slowly fading over trillions of years, not through a big crunch collapsing back to a singularity, but through a sudden, absolute transition to a universe with different laws of physics. The evidence is clear. Our universe is metastable. The Higgs field sits in a false vacuum. A true vacuum exists at lower energy. quantum mechanics permits tunneling between them. The mathematics suggests it's inevitable on long enough timescales, 10 to the 100 years, a number so large it's effectively infinite for any practical purpose. But that timescale assumes nothing disturbs the false vacuum. Black holes, high-energy collisions, unknown physics, or deliberate experimentation could trigger decay much sooner. We probably have billions of years, possibly trillions, maybe much longer, but probably isn't certainly. And the fact that we exist during a metastable period is either a remarkable coincidence or evidence for anthropic selection in a multiverse. The search for answers continues. Future colliders will refine measurements. Better theories might reveal unexpected stabilization mechanisms, or they might confirm our worst fears. For now, we live in a universe that seems stable but isn't. We exist during a temporary configuration of quantum fields, a pause between phase transitions, a moment when the laws of physics permit complexity, chemistry, and consciousness. This knowledge changes nothing about our daily lives. The sun will rise tomorrow, stars will shine for billions of years. The immediate future is secure, but the ultimate future? That remains uncertain. The universe is vast. The mysteries are endless. The journey continues. And somewhere, maybe in a distant galaxy, maybe in the quantum foam of space itself, a bubble might be forming, a region where the Higgs field has tunneled to its true value, a sphere of altered reality expanding at light speed. If so, we'll never know. One moment we exist, the next moment we're part of a different universe entirely. The void is stable, for now, but nothing lasts forever, not even the laws of physics themselves.